This demo shows how the semantic reasoning model developed in Convince can identify undesired situations at runtime. Semantic reasoning is based on semantic anchoring and an explicit knowledge representation with inference rule called scrub. The semantic anchoring is the process in the robot situation awareness pipeline that integrates numerical data coming from perception with information in digital twins to produce symbolic representation of the current and predicted observation of the operational environment. And the explicit knowledge representation is indeed the conceptualization of the system states, including undesired system states that correspond to known undesired situations that represent deviations faced by the robot with respect to the nominal operation conditions and or deviation with respect to the current progress of the task. So we are going to demonstrate semantic reasoning in a simple scenario with a robot in a simple scene with 3 rooms and objects and places in the rooms. There is no partial observability, so all the places and objects are already detected for simplicity. And the mission of the robot is basically to pick and place the objects which are not in the fridge, the soda, for example, in the kitchen table, and the snacks in the side table, and put them in the fridge. So the link between the virtual scene and the ontology is created by a JSON file, a configuration JSON file, which basically represents the mapping between the entities in the digital twin and their representation, their ontological representation in the knowledge graph. So for example, we have a fridge, which is the identifier used by PyRoboSim to model the fridge object. And with these statements, we basically declare that the fridge is of class storage object, where storage object is a concept in Scrub, the explicit knowledge representation at the core of the semantic reasoning model in Convince. Same here for kitchen table, for example. Kitchen table in PyRoboSim is mapped to a concept of a table in Scrub, and same for side table, for example, etc. So we basically initialize the ontology with a simple JSON file that creates the mapping between the objects in the virtual environment and the corresponding concepts in the ontology. Another component that we are using here in this demo are the monitors, the mood monitors from Convince. We are basically mimicking a force sensor on the robot, which is producing force reading of at the end of the robot arm. So this is simply generated with simple rules, so it's mimicking a force sensor. And with the monitors in Convince, we have this configuration, and basically we say that we are going to monitor the same topic here, and the action which is performed by the robot, and basically we have this rule. As soon as we do a place, we have a violation of the property if the effort is greater than 4.5 for more than 200 milliseconds. Good, so we can now start the task of the robot. So let's change some configuration in plot juggler, and basically we can command the robot with simple instructions like this. We provide Docker Compose commands for driving the robot. So we are basically asking now the robot to do a first part of the pick and place task we described at the beginning. So basically the robot has to go to fetch the soda and put the soda in the fridge. So it started going to the kitchen, and once the kitchen is reached, we go to the kitchen table and then we put the soda in the fridge. And now the robot goes to the dining room side table to fetch the snacks. You can see here from the force sensor, the simulated force sensor, that as soon as the robot has picked an object, the force at the end of the robot arm is increased, and the place actually make the force decreasing to a certain threshold. And for now, everything is okay because the force is below 4.5, which is the rule monitored by Moon. So at this point, where we have the robot has completed this first part, we are now going to inject a failure in the robot so that we can cause an undesired situation. And in this specific example, for simplicity, our injected failure concerned a spurious bug in the navigation system, which will make the robot to drift when reaching the fridge, ending with a position which is actually not in front of the fridge, but at the corner. And we also suppose that the programmer didn't program correctly the stop criteria for this navigation part, and will not detect that the robot is ended up at the corner of the fridge and not in front. So injecting this bug is simple like this, and then we continue with our mission after the bug is injected. So the robot now will reach the fridge, but actually will drift and will end up at the corner of the fridge trying to place the object and bump. It has bumped, the arm has bumped into the fridge because the robot was not in front. What happened is that now the force went above 4.5 and the monitor actually reacted. The reaction of the robot, of the monitor, actually triggered the execution of the semantic reasoning module, which has now all the informations to make some inference and see what is the problem that the robot is facing. So this is important because the monitor can only tell you the violation about the property. So it can tell you that while the place where it was done, something unexpected happened that caused it the force at the end of the robot rising above a certain tolerance. But for understanding what is the cause of the problem and apply the mitigation strategies, we need some runtime inference. That's the core point of the semantic reasoning module. So we can now inspect the knowledge of the robot at runtime with TypeDB Studio, so we can easily connect to our knowledge server. Everything is already set up for you in the software configuration that we provide, and we can browse queries. So let's have a look at the internal knowledge of the robot. So with this query, we are going to find all the entities, the positions, and their shapes for the object in the scene. This is just to give an overview of the complexity of the knowledge which is stored in the knowledge base. Even for this simple example, we have a lot of concepts, and we can find, for example, our table, the dining table, which has a shape, a box shape with weight, length, and date. But we can also find another table here, which is the side table, which has similar shape, and they have positions. Then we have storage object, which is a fridge with its position and the shape, and also for the object, the butter, the soda, the snacks, etc. And there is also the robot. So everything is actually modeled in the ontology thanks to the anchoring module. And now we can also have a look at the entities and their dispositions. So what the entity can do, can offer. For example, the robot has the capability that can place, and storage object like the fridge has the disposition of storage, and other objects have disposition of placeability, etc. So this dispositional model of the affordance is inspired by the SOMA ontology, and it's very useful for representing the causes of failure when performing actions. And here it is. This is, for example, the query that we can do to inspect the knowledge base, to basically find all the non-manifested affordances and their cause, the precondition violation. So what we get at this point here is that the place affordance, so there is a non-manifested affordance concerning the place affordance. This is normal because we were doing a place task, and we also have the information about which place task we were doing, involving an agent that can place and objects that have the disposition of placeability and storage, and the place affordance was defining the place action. What you see in green here actually is the inference made by the semantic reasoning module. So with the information received from the anchoring and the virtual scene, the inference has determined that the place affordance was not manifested, and the operational context was a situation with a precondition violation, and this precondition violation was caused by the fact that there is a required is in front of with respect to the agent and the target object. So basically you can inspect very easily the knowledge, and also the robot, of course, has this knowledge at runtime available that can be used by a planner to plan the next step to recover from the failure. So once again, our place affordance is not manifested because there has been a precondition violation, and the cause of this violation was are required is in front of between the agent and the target of the place affordance. Okay, so if now we pretend that this information has been made available to a planner and this was mapped into a known mitigation strategy to take an action to mitigate the problem. And for example, the problem could be mitigated by just doing another tour of the kitchen to recalibrate the robot. So we are now going to pretend that our next action will solve this spurious navigation bug, and so we are going to remove the injected bug in this way. And now we can finish our mission with the action that is determined by the planner, knowing what was the cause of the failure. So the mitigation strategy is going around for the kitchen to recalibrate and avoid the drift behavior, and then go to the fridge again, this time ending in front of the fridge. So this is a policy, this is a part of the policy that could be actuated by the planner after the inferred knowledge has been made available by the semantic reasoning model. So the task has completed correctly, and we can even force an update of the knowledge base with this command to check that now there are no more non-manifested affordances, and this is actually the case. And we can also check now if the agent is actually in front of the target location, and this is now the case. So given the information about the position of the entities in the scene, etc., the inference about the spatial relation between the agent and the fridge has determined that the robot is in front of the fridge. So this means the precondition is satisfied, and the place action indeed was completed correctly. That's all.